and base together, does it go this direction? Or when we mix them together, do the reactants largely remain unreacted? Some of you might know the answer already. For the rest of you, and for the rest of us, I guess I should say mere mortals, it's okay if you don't. Here's where we use pKa. Obviously, unless you have a photographic memory, you haven't memorized these pKa values yet. That's fine. But the pKa value for HF is 3.3. That's one of the values you need to put to memory. Well, what's the acid or acidity of a carboxylic acid? 4.75. So notice this was our acid, this was our base, this was our conjugate base. And this has a special role. It's known as our conjugate acid. To determine equilibrium, we just need to be able to identify the two acids, figure out which one is stronger. If you know these 8 values that I've asked you to memorize, you'll have time to memorize them over the next week and a half. You'll need these values because right now we have a tough decision to make. Which way does this reaction favor at equilibrium? It's either going to favor the right or it's going to favor the left. Now, all we need to know is which one of the acids that we're looking at is stronger. And acid-base reactions always go from stronger to weaker reagents. In this particular case, these two species, acid and base, when they react with one another, they dissociate more going this direction than the reverse happens. So at equilibrium, this reaction favors the right-hand side. Let's do another problem like this right away. Again, this is just by comparing the two acids. If we can find the stronger acid, the lower number means the reaction goes the other direction. Let's do another one. Give us practice on all these particular things. We're going to use acetate again. Let's use water this time. Let's use water playing a role as acid. Let's use acetate playing the role as base. And for right now, maybe it's okay when we look at these two things. Maybe you don't know which one's the stronger acid, which one's the base, but one of these two species has a hydrogen on it. And this one, this group here, we know is not acidic at all, this methyl group here. But maybe you don't know. It's okay. But I'm going to tell us, anyway, this is our acid that I want you to evaluate. This is our base. And I want you to do those arrow pushing exercises again. Okay? Start with that. Draw the resulting conjugate acids, conjugate bases. And finally, at the end of this exercise, we'll evaluate which way the equilibrium lies. Again, next 60 seconds or so, you should be drawing arrows between these two things. I said one's base, one's acid. How do the arrows move? If you don't know, you should at least be able to say, well, this is acid. What's its conjugate base look like? This is the base. What's its conjugate acid look like? You should be able to do something with this. You shouldn't be sitting there staring at it, wondering, panicking, in a cold sweat, wondering what to do. You should be able to take some steps, some decisive, definitive forward action on your own. Either push some arrows, or start drawing some conjugate bases and conjugate acids. You're all capable of one of those two tasks that I've taught you today. I'll catch up with you in about 20 seconds or so. Take this problem as far forward as you can. If you can ultimately figure out which direction the reaction lies at equilibrium, that's great. That's where we're aiming to go with this. First, practice arrows, conjugate acids, conjugate bases. See if you recall pKa's or look back in your notes when you identify the two acids in the reaction. See if you can figure out which direction this reaction goes at equilibrium. I'm going to get started now and catch up with you. I'll use a red pen. The base reacts with the proton on our acid, and you could have picked this one or this one. They're equal. We're going to form a new bond between these two. We're going to break a bond between these two. We'll end up making hydroxide. If you drew hydroxide on the right instead of the left, it's absolutely fine. We'll have a sodium ion associated with it. I don't care too much about that. This is acting as a base, picks up a proton. When we draw the resulting product of this reaction, we know that it'll be its conjugate acid. So water was the acid. This is its conjugate base. Sorry about my handwriting here. It's conjugate base. This is conjugate acid. So we know what the two acids are. And if we compare these two acids, then we can determine the direction of this reaction at equilibrium. Again, if this is confusing how I got to these two things, then you need to go back and really restudy drawing these particular notes. I did these two examples kind of really close by one another to see that things change drastically, or can change drastically depending on my choice of acid. pKa of water is 15.7. Carboxylic acid or acetic acid vinegar is 4.75. This is our stronger acid in the pair of these two things. So you mix water and sodium acetate together, and they start forming sodium hydroxide and acetic acid. But this is the much stronger acid compared to it, and at equilibrium, when you mix these two things together, largely you'll have these two species as the major things, and these two species will be the minor things. These two things, they don't appreciably react with one another. When you mix these two things together, they form a stronger acid than what we started with. That doesn't make any sense. So stronger acid is always going to favor the weaker acid in weaker reagents. This is actually true when we look at the conjugate base theory, and I'm just going to spend 2 minutes on this. It's not the important part. The important part is pKa's. But we note in this particular reaction based on pKa that this is the stronger acid. Well, which one of these two is the stronger base? This is the stronger acid out of these two. So its conjugate base will be the weaker base. This is the weaker acid, and its base will be the stronger base. This follows from this idea that strong acids have weak bases. The weaker acid has a strong base. It'll always be the case that the stronger acid and the stronger base will be on the same side of the equilibrium reaction, and they will always go the opposite direction. The same is true up above. The stronger acid is this one, the stronger base is this one, and it goes this particular direction. We have like 2-3 more minutes left of our time here in lecture. I'm going to open up to any questions that there are, but then again, just to reiterate, at 11:05, we'll have